Welcome back, everyone. I'd like to introduce our next speaker, which is Dewni Pathegama from TOPTICA. She's basically replacing Rafael Wilk, who was on the schedule initially. So we're very glad to have her here. And she's going to talk to us about ultra-stable lasers in high finesse cavities. The floor is yours.
Thank you. Yeah, so for the next 1 hour, we'll be talking about ultra-stable lasers based on high finesse cavities. Where do I point? Yeah, perfect. Okay, so a little motivation first as to why we need ultra-stable lasers. Many quantum atomic and nuclear physics of experiments need lasers as a central tool. For example, in spectroscopic measurements, as you have heard several times in the last few presentations as well, to get to a narrow resolution line width of the transition, you need longer interaction time with the atoms of the laser. And then, so for example, if you want to resolve a line width of 1 Hertz for an atomic transition, you need to probe the transition for at least 1 second. So you need a laser that has at least 1 second long coherence time. And then for quantum information experiments, where the goal is to perform as many gate operations as possible over a longer period of time at a stretch, you also need lasers with long coherence times, ideally of about 1 second or slightly above. But the problem we have now is the current best lasers out of the box have coherent times of a few milliseconds. So you see the challenge is to bring this down several orders of magnitude to a few seconds so that we can use the lasers for the experiments. So how do we do this? Coherence time depends on the phase noise of your laser. So less phase noise, longer coherence time. So one way of getting to a longer coherence time by decreasing the phase noise of the laser is to stabilize its frequency, because frequency noise and phase noise are two sides of the same coin. So you stabilize your frequency noise and then you get low phase noise, therefore longer coherence time. So one way of doing this is to compare the frequency of your laser with a stable frequency reference from which you get some information of how detuned your laser frequency is from the reference frequency. And this you can use to generate an error signal that can be used to generate control signals to manipulate some actuator that can change the laser frequency. For example, for when it comes to diode lasers, you can use the piezo voltage and the diode current that can change the laser frequency. For fiber lasers, you can use the piezo voltage and the temperature of the laser to change frequency. So what can we use as references? First is the most stable frequency reference of nature, the atomic transitions. Second is the ultra-stable optical cavity. So today in this talk, we will focus on the second one, how to use an optical cavity to get to a stable laser. So a quick agenda before we start. I will first introduce what optical cavities are and how they work. Then we'll talk about how to stabilize your laser frequency by using this optical cavity. And then we will talk about what limits the performance of your cavity-locked laser. And finally, I will show you some state-of-the-art technologies that are being investigated in research groups around the world currently. Okay, so we start with some basic physics. This must be all familiar to you already. So as Thorsten said yesterday, if you're bored, just yawn and I'll skip ahead. So optical cavities, or more specifically Fabry-Perot cavities, are just two mirrors separated by a certain distance facing each other. And any light that enters this cavity or laser beam that enters this cavity can bounce back and forth between the two mirrors, forming a standing wave. And for this, the laser beam that enters the cavity has to fulfill some resonance condition. So here in this diagram, you see a typical Fabry-Perot cavity, which is made of one planar mirror and one curved mirror, which is typically used because it's the most stable cavity configuration. So the stability of optical cavities, there's a whole physics behind it, which is a little bit out of the scope of this talk. So I'll just stop at saying that it's the most stable configuration. So the resonance condition that light has to fulfill for it to generate a standing wave inside the cavity is that the round trip path inside the cavity should be equal to an integer multiple of the wavelength of the light that's going inside. So you see that for a fixed cavity length, the same mode can be excited inside the cavity for several wavelengths of light. And these modes are then separated in frequency by what we call the free spectral range. The free spectral range equation here is defined by the length of the cavity. The third more important factor when it comes to cavities is its finesse, which is a measure of how long a photon can bounce back and forth between the two mirrors before it's transmitted from the cavity. So obviously this is then defined by the reflectivities of the cavity mirrors. Therefore, fixed free spectral range and fixed mirror reflectivities, and therefore a fixed finesse. The line width of the cavity is defined as the free spectral range divided by the finesse. So here in this diagram, you see the transmission spectrum of a cavity, or for two cavities with different finesse. And you see that the transmission is has a certain width. The halfway point of this width, or the full width at half maximum point, is called the line width of the cavity. So assuming you have a cavity that has a length of 10 centimeters, which translates to a free spectral range of 1.5 gigahertz, for a finesse of 100, you get a line width of 15 megahertz. And for a finesse of 200,000, you get a line width of 7.5 kilohertz. So depending on the finesse and depending on the reflectivity of your mirrors, you can decrease the line width of your cavity, which is good because higher the finesse, narrower the cavity line width, and therefore lower uncertainty you have when you stabilize your laser frequency to this cavity resonance frequency. Okay, so now we come to the second part. How do we stabilize our laser frequency to a cavity? There are, of course, several ways, but today we focus on one of the most common and one of the best methods of doing this, pound-river Hall locking. So first, I will give you some intuitive introduction to pound-river Hall locking. So intuitively, when you want to lock your laser to a cavity resonance, what you think of is to use the transmission from the cavity and lock your laser to either top of this fringe or to a side of this fringe. So if your laser is now locked to the cavity transmission and your frequency drifts away from the resonance, the intensity of transmission will drop because less laser light is coupled into the cavity. So by looking at the intensity of transmission, you get an idea about how different your frequency, your laser frequency is from the cavity's resonance frequency. But the problem in this scheme is that it can't distinguish between intensity drops in the cavity transmission caused by frequency fluctuations of your laser and intensity fluctuations of your laser itself. So to overcome this, one thing we can do is to measure the reflected beam and hold this at 0. Because as you see from the graph here, the reflected intensity of the beam from the cavity will be 0 if the laser is at resonance with the cavity, because all of the light will be coupled into the cavity and the reflected beam would be 0. But the problem here is that, as you see, the reflected intensity is symmetric around resonance. So if you're at this point at resonance and then your laser frequency drifts to this side or this side, you can't tell by looking at the intensity because in both cases it will increase. But instead what we can do is measure the phase of the reflected beam, because as you see at resonance the phase disappears because there's no reflected beam, and around resonance the phase has opposite signs. So by looking at this phase shift of the reflected beam, you can get an idea about how different your laser frequency is, and then your control loop can drag the frequency back to the resonance frequency. So again, the problem, you can't measure phase directly. You can only measure phase of a beam relative to something else. So what do? You have your incident beam with a laser frequency of, let's say, phi, and for argument's sake, with a 0 phase. Close to resonance, your incident beam gets coupled into the cavity, makes a round trip, and then some of it will leak back from the first cavity mirror. The leaked beam will have a phase shift that's acquired through its round trip inside the cavity. So this is what we want to measure. So what do we measure this against? We make 2 extra beams that also are incident on the cavity, but they're so far away from the cavity line width that when your laser frequency is near resonance, your main beam, so this one will get coupled into the cavity, and these 2, because they're far away from resonance, they will get directly reflected back from the first mirror. So as they get reflected back, they acquire phase shift of 180 degrees, but now you have 3 beams, 2 of them with similar phase, so your 2 beams that are directly reflected, and your main beam that you want to measure that has a phase shift. So by combining these 3 beams, for example, at a photodiode to create a beat knot between the signals, you get a signal that gives you the phase information of your laser frequencies detuning from the resonance frequency of the cavity. So this is exactly what we do in boundary over Hall locking. We phase modulate our laser beam that's going into the cavity, creating a carrier and 2 sidebands. And you choose your modulation frequency so that the 2 sidebands are so far away from the carrier that near resonance, the carrier gets coupled into the cavity and the 2 sidebands will get completely reflected back from the first cavity mirror. So by mixing the 2 sidebands and the leaked carrier near resonance with each other, you can generate an error signal that contains the information that you need to change your laser frequency to keep it locked to the resonance frequency of the cavity. So again, I will not go into a lot of details about this, but there's a very nice paper from Eric Black in 2001 that has a very detailed description of boundary over Hall locking, what it's used for, and all the mathematical derivations that you can read if you're interested. But here you see the error signal that's generated by this method, and you see that the steepness of your error signal depends on your cavity line width. So as we said earlier, lower the line width, more steeper your error signal is, and therefore better locking point you have. And then as also here in the equation, when your laser is locked to the cavity, the fractional frequency changes of your laser are determined by the fractional length changes of your cavity. So this is how we do it in practice. You have your laser. We use an electro-optic modulator to phase modulate the light, which is then directed into the cavity, and we use a combination of a quarter wave plate and a polarizing beam splitter to pick up the reflected beam. And this is then sent onto a photodiode to generate the mixing products of the carrier with the 2 sidebands. This is then mixed down with the same frequency as the modulation frequency, then generating 2 signals at DC and 1 high frequency component. So this DC signal is what we want to use as the error signal, which we isolate using a low-pass filter. And then this you can send to, for example, a PID controller to generate the control signals for the laser. Okay, so as I mentioned, when your laser is locked to the cavity, the frequency changes or the fractional frequency stability of your laser is determined by the fractional length stability of your cavity. So the challenge here is to keep your cavity as stable as possible in terms of its length. And as I mentioned, a typical Fabry-Perot cavity is just 2 mirrors facing each other in air. But this is already a restriction towards length stability. So to overcome this, we take our cavity mirrors and then optically contact them onto a glass spacer to give a first order of lens stability. And then this optically contacted mirror and the spacer forms one solid block of material that's of course affected by environmental factors like pressure and temperature fluctuations and vibrations. And the next step towards stabilizing the length of the cavity then is to shield it from all these environmental factors. So this is what we will talk about in the next few slides. Okay, now we come to the factors that limit the lens stability of our cavity. The first one is environmental pressure fluctuations. So from the famous Edlund equations of refractive index, we know that the refractivity of a material depends on the pressure. And we also know that the optical path length of light through a material depends on its refractive index. So if any pressure changes that change the refractive index of material will change the optical path length of light through that material. And this will directly translate into frequency instability of our laser. For example, it has been shown that fractional pressure changes as small as 10 to the minus 3 can create a fractional frequency instability of lasers of approximately 3 times 10 to the minus 10, which is well above the stability we expect from our lasers, which is in the order of 10 to the minus 15, 10 to the minus 16. So in this range, to get to this range of frequency stability, we need to shield the cavity from pressure fluctuations as small as 10 to the minus 8 to 10 to the minus 9. So how do we achieve this? We place the cavity in high vacuum to shield it from pressure fluctuations. So the second factor that limits the length stability of a cavity is vibrations and acceleration forces. This has two types. First one is the gravitational acceleration induced mirror tilts. So a beam that's held at its center tends to sag at its ends, bending the beam. So if this is our spacer now, and the two mirrors are contacted on either side, this bending will create a tilt in the mirrors, which will change the optical path length of light through the cavity. This is the same if the cavity or the spacer is held at its ends, that it tends to sag at the center, already bending the mirrors again. The solution for this is to mount the cavity at its airy points, which are the points that minimize the bending due to gravity. So when it's mounted at airy points, it will still bend at some places, but the ends of the beam will still be kept parallel to each other. So we get rid of the mirror tilt. The second type is forces coupled to the system that accelerate the system. This has again two effects from the elastic deformation of materials under forces and Poisson's effect. So for example, if you consider a vertically mounted cavity that's held at its bottom and you have a acceleration in the vertical direction, this will cause the spacer to contract at the top due to elastic deformation, and it will cause it to expand at the sides due to Poisson's effect, so in the perpendicular direction of the force applied. This is the same if the cavity is held at its top. And the way to avoid this is to mount the cavity at its symmetry plane, because in this case, a vertical acceleration will cause the cavity to contract at the top and expand at the bottom, effectively canceling the two effects out. So how do we get rid of vibrations that cause deformations of your cavity? First is to use a vibration isolation table that can, so this is done using finite element modeling. So you have your cavity modeled and then you apply several vibration effects. So this goes for both vibration effects from gravity and for accelerations. And then you can find the points where the bending is minimum in all these vibrations, and then you mount your cavity at these points. Yeah, so vibration isolation table to shield the cavity from vibrations to some extent, and to get rid of the vibration noise, residual vibration noise, you can make your cavity insensitive to vibrations by changing its geometry and mounting methods. So here you see some attempts at doing this. For example, the vertically mounted cavity from the group at Gila. The cavity is vertically mounted to make it insensitive to gravitational effects. So even if it sags due to gravity, the optical axis is along the vertical axis, so it has no effect on the optical path length. And it's supported at its center to make it insensitive to other external accelerations. The second one is a cavity with cutouts at the bottom, which is mounted horizontally in its symmetry planes, again, to make it insensitive to accelerations. And these cutouts at its bottom make it insensitive to, or partially insensitive to vertical vibrations. Third one is a horizontally mounted cavity from PTB. This has 10 mounting points, 6 at its symmetry planes, and 4 at the airy points of the cavity. So I should mention here that this one is meant to be a transportable cavity, which is why it has such a sophisticated mounting system, which is a little bit overdefined, but it helps when the cavity is being transported, because then you introduce extra vibrations through transportation. All right, and the third factor is environmental temperature. So we know that the effect of changing temperature on the length of a material depends on its coefficient of thermal expansion. Coefficient of thermal expansion also depends on temperature. So by changing the temperature you operate the system at, you change the coefficient of thermal expansion, and so you can change how much your cavity is subjected to changes from the environmental temperature. There are some materials that have a coefficient of thermal expansion that crosses 0 at certain temperatures. The most common one is ultra-low expansion glass. You see here the coefficient of thermal expansion for ULE, or ultra-low expansion glass, and you see here that around 20 degrees, 20 degrees Celsius, it crosses 0. So if alpha is 0, then you have minimum thermal expansion due to temperature fluctuations. It's also clear from this one, which shows the thermal expansion in parts per million for ULE glass. And you see that for a certain temperature range around 20 degrees, the thermal expansion is minimum. This is also another positive aspect of ULE glass, that the CTE change with temperature is rather flat compared to other materials. So even if you're not directly at the zero crossing CTE, but slightly above or below it, your thermal expansions will still be minimum. So how do you achieve minimum thermal expansions in your cavity? You maintain your system at the 0 crossing temperature by using active and passive temperature control. So the next factor is thermal noise, which is related to temperature noise as well, but in a more microscopic zone. Thermal noise has several different components. First one is photothermal noise, which is optical power-induced instability. So we always have some laser light going into the cavity and oscillating back and forth inside the cavity. So the cavity materials will always absorb some of this laser power and convert this to heat. And this is what causes the photothermal noise. If your laser power is fluctuating, the amount of power absorbed by the cavity materials will also fluctuate, creating a heat gradient that can lead to expansion in the cavity materials. The way to avoid this is to stabilize the power of your laser beam. And we do this very simply by splitting off some light before it enters the cavity, directing it towards the photodiode, and using this photodiode signal to keep your laser power locked to a set point. You do this by generating a control signal that changes the power in the RF frequency that drives the your acousto-optic modulator in the beam path that will change the power in the diffracted or diffracted mode. Yes. So yes, it depends a little bit of everything else that you have in your system. For example, if you have an electro-optic modulator, having this kind of scheme, if you have the, sorry. Actually, no, it doesn't actually make sense. So you can do it before and after the cavity transmission. It doesn't really make a big difference. Doing it after the cavity transmission makes sure that you also compensate for power fluctuations and beam pointing on your breadboard that you use in front of the cavity. But if you do it just before the light enters the cavity, then you only have so many uncompensated beam paths that you can neglect the effect from this. All right, so the next component of thermal noise is thermo-optic noise. So even if your cavity is now stabilized at a set temperature, there would still be some localized thermodynamic temperature fluctuations that can still lead to some thermoelastic noise, which is the expansion of the cavity materials due to temperature fluctuations, and thermorefractive noise, which is the change in the refractive index of the material due to temperature fluctuations. So both of these effects will also change the optical path length. And this has contributions from all three components of the cavity, so the spacer, the mirror substrates, and the coating. But the thermorefractive noise only affects the cavity materials that interact with light. So this then excludes the spacer because spacer doesn't directly interact with light. And this includes the thermorefractive noise component from the substrate because even though the substrate interacts with light, this is only when the light enters the cavity and leaves the cavity. So relative to the thermoelastic noise from the substrate, the thermorefractive noise can be considered negligible. So the total thermo-optic noise in the system is from the thermoelastic noise component from the spacer, thermoelastic noise component from the two substrates, and the thermo-optic noise from the coating. So thermo-optic noise depends on the CTE, so the zero crossing temperature, coefficient of thermal expansion, and material qualities like thermal conductivity, density, and heat capacity of the material. So to fight thermo-optic noise, operating your system at zero crossing CT already helps. And to further reduce it, you can choose your cavity materials, for example, so that they have less thermal conductivity. So choosing your cavity materials plays a big role in reducing thermal noise, which we will talk about in a little bit. Before that, we get to the last component of thermal noise, thermomechanical noise that's caused by the Brownian motion of the atoms in the cavity materials. So Brownian motion is the vibrations of the cavity materials or the atoms of the cavity materials that's caused by heat and random vibrations of the material. And of course, it has also contributions from all three components. So from the spacer, from the substrate, and the coating. So here you see the power spectral density of Brownian noise caused by each cavity material, which is derived from fluctuation dissipation theorem, but we will not go into too much details about this. Instead, we will focus on the highlighted values, which are the values that we can manipulate in our cavity. For example, you see that all three contributions depend on the temperature. For the spacer and the substrate, this is the average temperature your cavity is operated at. And for the coating, this is the combination of the average temperature and the heat that's introduced by the light that's oscillating inside the cavity. And then you see that the spacer contribution also depends on the length of the cavity. So longer your cavity is, less Brownian noise contribution it has. Similarly, the substrate and the coating contribution depends on the width of the beam mode inside on the mirrors. So bigger the beam width, lower the Brownian noise contribution from these two components. And then finally, all three contributions depend on the mechanical loss angle of the material, so which is a measure of how much the material can dampen internal vibrations. So of course, for lower mechanical loss angle, lower Brownian noise you have from each of the components. Okay, so it's clear that the way to decrease the thermal noise in your system is to choose your cavity materials so that they have inherently less thermal noise. So first we focus on the spacer and the mirror substrates. As you saw, both contributions depend on the average temperature. So lower the temperature, lower the thermal noise caused by the materials. And one way to get to lower thermal noise then is to go to very low temperatures, so cryogenic temperatures. In this case, we can choose crystalline materials like silicon and sapphire, which has the advantage that they have zero crossing CTE at cryogenic temperatures like 17 and 124 Kelvin for silicon and 4 Kelvin for sapphire. So you have so by operating at cryogenic temperatures, you get lower thermal noise due to Brownian noise and lower effects from temperature fluctuations because you are at zero crossing CTE. And then we focus on mechanical loss angle. For this, you can replace the typically used materials, so ultra-low expansion glass with, for example, fused silica, which has several orders of magnitude lower mechanical loss angle at room temperature. Or you can switch to, again, crystalline materials like silicon and sapphire, which have lower mechanical loss angle at cryogenic temperatures. And then you have a win-win-win case because you have less noise because you have lower mechanical loss angle. You have less noise because you're at cryogenic temperatures, and you have lower effects from thermal fluctuations because you're at zero CTE. But of course, operating at cryogenic temperatures, it is not the easiest task because you need a sophisticated cooling system to keep your system at very low temperatures, which then introduces some vibration noise to the system. So you also need a sophisticated vibration isolation system. Okay, so the third one is the width of the mode on the two mirrors. So higher the mode width, lower the Brownian noise. And to increase the mode width, you can increase the length of the spacer. This also has the advantage that increased spacer length leads to lower Brownian noise as well. But then again, longer your cavity is, more susceptible it is to vibration noise. So you need you need sophisticated vibration isolation systems. All right, so let's assume that we stick to a cheaper to produce and an easier to maintain system. So we use a short ULE spacer, which we can operate at room temperature and relatively vibration insensitive. In this case, the fundamental limit to your thermal noise is given by the coatings. To overcome this, something that has been investigated very recently is to use crystalline mirror coatings for the cavity. It has been shown that as opposed to dielectric coatings, which is more common, crystalline coatings have 1 order of magnitude lower mechanical loss angle at room temperatures. And by using crystalline coatings in your cavity, as recently as 2013, they have shown that you get 10 times less Brownian noise. But it should also be mentioned, though, that crystalline coatings are only available for infrared light because they are highly absorbing at visible wavelengths. Okay, so now you have an ultrastable laser. that's locked to an auto-stable cavity, shielded from all environmental factors. Now you want to take some light off from your laser and send it to your experiment. You would use fibers for this. So any laser beam that's traveling through a fiber acquires some phase shift due to any stress in fiber caused by fluctuations in temperature, pressure, mechanical stress, and airflow near the fiber. This you see here. So you have your laser beam with your ultra-stable frequency coming out, and then it goes through a fiber, acquires some phase shift, and at your experiment, you have your laser frequency that's broadened with fiber noise. So you need to get rid of this. How do you do this? By using active fiber noise cancellation. For this, you use the famous Michelson interferometer. You split off some light from your laser, send it to a reference mirror, and then send it back onto a photodiode. This forms one arm of your Michelson interferometer. And the transmitted beam from the beam splitter then is sent through an acousto-optic modulator into the fiber and towards your experiment. On the other side of the fiber, you have a back reflecting mirror that can reflect back some of the light back through the fiber and the AOM onto the photodiode, forming the second arm of the interferometer. So at your photodiode, then you make a beat node that's the difference between the reference arm with your laser frequency and your experiment arm, let's say, with the laser frequency shifted by the AOM frequency 2 times as it makes a round trip through the AOM, and the fiber the phase shift acquired inside the fiber. This you can then send to a phase-locked loop along with the reference signal to compensate for the fiber noise. So how do you do this? Inside the phase-locked loop is a phase detector to which we give our beat node from the interferometer, which is now at 2 times the AOM frequency coming from here, and 2 times the fiber noise acquired by the beam going 2 times through the fiber. Of course, the frequency of the laser gets canceled out. And then as the reference signal, we give 2 times the AOM frequency. So at the output from the phase detector, you only have the phase noise that's given to the laser beam by the fiber. So this phase shift then you can use as a, so these are of course all electronic signals. So this you can use as a input to a PID controller, for example, to generate a control signal that can change the frequency of the your AOM, or the frequency of the RF signal that drives your AOM, that can then change the frequency of your diffracted mode from the AOM, compensating for any phase shifts. All right. So as we now shift to the next part of the talk, now would be a good time if you have any questions. Yes. Mm-hmm. Yeah. Yeah. Yes, so this is possible, but the problem would be that you never really know the how much the phase shift is, or how much the phase is of the incident beam. So the idea behind creating sidebands with a set phase is that you know what you're comparing against, so you know exactly how much the phase is shifted inside the cavity. Yes.
Again, but the benefits are having your catheter. facing upright or horizontal?
Uh,
Explain it once, but,
so for vibration, noise. So if you're vertically mounted, so your optical axis would be here, right? You have the two mirrors. And if you're vertically mounted, your optical axis is always insensitive to vertical vibrations. So vertical accelerations caused by, for example, gravity. So it could be that your cavity is slightly deformed due to gravity, but your optical axis will always be insensitive to this. This is the advantage of having a cavity vertically mounted. So, for example, here, what I said about if your cavity is mounted at the center, the gravity will tend to sag it at the ends, and if it's mounted at the sides, it will tend to sag at the center. So one option is to mount at airy points, so you are insensitive to this. And the other option is to mount it vertically, so your optical axis itself is insensitive to any sags due to gravity. So here they are not mounting at airy points to get rid of gravitational acceleration induced bending. They are only mounting it vertically. And the support at the center is that so that you compensate for change deformations in the cavity due to this effect.
So then the ones have to deal with the airy.
Yeah, so if your cavity is horizontally mounted, usually you mount it at the airy points to deal with the gravitational effects. And
Every mounting not getting rid of the gravitation right? Or no.
so yes, in a sense, if you have a long beam, even if you're mounted at the airy points, your beam will still tend to bend. But the point with the airy points is that it always keeps the two ends parallel to each other. Yeah. Because if the mirrors are parallel, the optical path length would still be the same. But if the mirrors are bent like this or like this will change the optical axis.
Gravitation on one mirror that's maybe like and
what do you mean by self-deforming?
I mean, just as the ULE cavity can form on weight, the mirrors themselves also can deform, right? So when they're upright, they can like sag down.
Yeah, of course. So this is still a problem, but compared to the spacer length, the length of the mirrors are very small. So of course, the coating bending doesn't have a big effect because the coating is very thin. The only effect of this sort would be from the mirror substrate that they bend somehow. But this is still negligible compared to the spacer bending because of the length of the spacer.
Fiber noise cancellation. Which level of precision of the laser we need a fiber noise cancellation? For example, if you want to send 5 meter, still we need it, or just for the long transfer?
Well, of course, it matters more for the longer fibers because you add more noise. But for example, we have seen from our experiments that a fiber as short as 10 meters, I think, is the shortest that we have. It still adds a few kilohertz of fiber noise. So your laser that's ideally at a hertz line width still is broadened by a few kilohertz due to fiber noise. So this still you need to cancel. I mean, depends also a little bit on your application. So where you take your light to, if you need a hertz line width, you do need to cancel this kilohertz noise. But if you only need few hundred kilohertz of line width from your laser, then you don't care. All right. So now you have an ultra-stable laser system. Or, well, you have a laser that you lock to a stable cavity to get the laser frequency stable, in which case the cavity translates its length stability to the frequency stability of your laser. So to get rid of, to make your cavity as stable as possible, we use passive and active temperature control. We put it inside a vacuum to shield it from temperature fluctuations. We put it on a vibration isolation table, and to get rid of acoustic noise, we put the whole system inside an acoustic isolation box. Now you split off some light to your experiment, and you realize it adds some frequency noise from the fibers, so you use active fiber noise cancellation to get your stable laser light to your experiment. So now you have an ultra-stable laser system, but how do you know how stable your system is? So what we can do is to compare the laser frequency of my laser with a frequency reference. And through this comparison, you make a beat note that's the frequency difference between my laser and the reference that can be counted using a frequency counter and post-process to find out how stable the frequency is for this beat note. So in the case that you have a perfect reference laser, if you assume that your reference doesn't have any frequency noise, the noise that you calculate here would be the noise of your laser. In the case you have an identical laser to your laser, you can assume that both of them have the same amount of noise. So you distribute the calculated frequency noise between the two lasers to find out the noise of your laser. But of course, these two are only identical cases, and this is impossible in real life because you never have lasers with zero noise, and you can never find a laser that's exactly identical to yours. So in this case, what you can do to find the absolute stability of your laser is to compare it against two other lasers. We call this a three-corner hat measurement because you have three systems and you compare each system against each other. And then you have three stability measurements from the three lasers. And through some post-processing, you can calculate how stable your laser is. So some theory again, how do we qualify the stability of a cavity locked laser, or in more generally, how do we qualify the stability of an oscillator? I think this is again familiar territory for most of you. In time domain, we use Allen variance. Mm-hmm. So this measurements here is always with the beat notes that we get by overlapping the two beams from the two lasers. And what we measure is the noise of this beat note. So this will always be the combination of the two lasers then. So the noise from both lasers combined together. And usually if you look at the stability, so if you plot the stability and you look at the noise, of course it's dominated more by the noisier laser. So this is why you can never really see how good your laser is, because if it's less noisier than the reference you are using, then your stability that you measure is always dominated by the reference. So this is why you need to measure it against three lasers, so you can measure the absolute stability. But of course, it's also possible that if you know how good your reference laser is, if you know what kind of noises affect your reference, you can assume how good your laser is against the reference, because if you have more noise in a certain frequency region and you know that this is caused by your reference, you can more or less say, okay, this is caused by my reference, so my laser should be better than this. Yeah, so to qualify the stability of an oscillator, we use in time domain Allen variance, which is analogous to standard variance in statistics, except Allen variance takes into account the time dependence of your data or your noise. So what it does is it calculates the difference between, so from here, it calculates the difference between two successive samples and then calculates the variance of these differences. So by looking at the Allen variance, you can tell how much your samples vary from each other. In your case, or in our case, the samples are the fractional frequency changes of your laser averaged over a certain time. So if you now look at the Allen variance, you see how much your frequency differs from time to time inside these averaging times. So Allen variance then gives the frequency instability of your laser with time. And then to Allen deviation, which is the most commonly used measure, as in standard deviation, you take the square root of Allen variance. So this is in time domain. In frequency domain, we take the Fourier transforms or the power spectral density. And as you're familiar, it can be approximated using the power law, where alpha here in the equation is an integer that models the most appropriate power law for your data. So by looking at a certain F alpha dependence on your data, you can always tell what kind of noise you have in your system, and then you know how you can fight against this. So here you also see the famous sigma tau diagram. For example, if your F alpha dependence is alpha is at 1, so you have a in time domain you have a tau minus 1 slope on your noise. You know that this comes from white phase noise, which is caused by, for example, electronic noise that appears at lower averaging times, which then gets averaged down to 0 at longer averaging times. So what does this all come down to? Here you see a typical stability measurement from one of our lasers at TOPTICA, or one of our Hertz lasers at TOPTICA. And you see that we reach a fractional frequency instability of below 1 × 10⁻⁻15 up to around 10 seconds of averaging times. So since you don't have any comparison data for this now, let's keep this number in mind as I show you some state-of-the-art technologies that are being investigated in research groups around the world. The first one is a cubic cavity that's 5 centimeters long, made of ultra-low expansion glass, meant for space applications from the National Metrology Institute in UK. It has a symmetric design, as you see, with a tetrahedral support, which makes it very insensitive to acceleration noise. And the interesting fact about this system is that laser locking remains stable even when the cavity is inverted due to its symmetric design, which is a big plus point for space applications. So with this system, they reach a fractional frequency instability of 5 × 10⁻16, around 1 second averaging times. The second one is a cryogenic silicon cavity from the groups at GILA and PTB. This is made from a single silicon crystal, and it's operated at 124 Kelvin. So at the temperature where silicon has a zero crossing CTE. And they have that advantage that at cryogenic temperatures, they can decrease the Brownian noise due to silicon having very low mechanical loss at these temperatures. They also mount the cavity vertically to increase the vibration insensitivity, and they reach a frequency instability of approximately 5 times 10 to the minus 17 up to 10 seconds of averaging times. The fourth one is a transportable cavity that I also showed you earlier, that's operated at room temperature, also from PTB. They have this special mounting system with 10 mounting points to increase the vibration sensitivity during transportation. The cavity has crystalline mirror coatings to decrease the thermal noise, few silica substrates and ULE spacer. And with this, they reach a fractional frequency instability of 1.6 times 10 to the minus 16 at 1 second, which as of last year was the I think still up to now is the best instability reached by transportable cavity systems so far. The last one is a long cavity, a 48 centimeter cavity operated also at room temperature from a different group at PTB. So long cavity length to lower the thermal noise again, and to battle with the vibration sensitivity that's caused by the longer length, they use a self-balancing mounting. And with this, they reach fractional frequency instabilities below 1 times 10 to the minus 16 up to 1,000 seconds of averaging times. So let's quickly go back now here. So this being a commercial system still reaches, it's about 2 orders of magnitude lower instability than, or higher instability than the best cavities that we have so far today. But in my completely unbiased opinion, it's still very impressive that commercial systems reach this kind of stability, considering that they have to be careful about vibration sensitivity during transportation and also reproductivity of these systems, especially during small windows of time. All right, so that's the end of my talk. So in a short summary, we talked about why we need ultra-stable lasers and how to stabilize a laser to an optical cavity. And for a cavity locked laser, what limits its performance, and how good the current ultra-stable lasers are. So clearly there's still a lot of room for improvement, and there's a lot of research going on right now. But I think currently we are already at a very good point in the research when it comes to ultra-stable lasers. Thank you.
Okay, if anybody have any extra questions, I think a lot of questions have been asked during the talk, but probably anybody want to ask more?
Can you go to this slide where you explain the thermal noise and the stabilization of thermal noise with a PID on AOM?
This one?
Yes. In this particular setup, even I didn't understand, even if you stabilize the power going into the cavity, there's like a fixed amount of power that goes into the cavity. Even after stabilization, the power will still be absorbed by the mirrors, right?
Yes.
So how does that really help us stabilizing the power, because the power is still getting absorbed?
Yes. So by stabilizing the power of the laser, you, to a big extent, you decrease the thermal noise caused by power fluctuations. And of course, there's the fundamental limits, one caused by the shot noise of the optical beam, so due to quantum nature of the photons. And this is the fundamental noise to photothermal noise. And the other limit is this Brownian noise. So Brownian noise is 2 types: random vibrations of the atoms and vibrations of the atoms caused by temperature or heat. And this part is always there because we have light inside the cavity, and that heats up the coatings, causing Brownian noise in the coatings.
Okay, any other questions? Please.
Hi. So, in your slide with the Allen deviation, you had commented on the parameter of alpha in the power spectral density. Yeah, could you repeat that comment once again about the choice of alpha or the alpha parameter in the spectral density?
Yeah. So this equation comes from power law, which says that for every noise type you have, there's a certain power that can be approximated. And alpha is just an integer that models the most appropriate power law for the type of noise that you have. This is why looking at the F alpha dependence in your noise, you can tell what kind of noise you have in your system.
Okay, so does this mean that whenever you are trying to get your power spectral density, you should, depending on what noise you are interested in, you will model that with your choice of alpha?
It's more the other way around. You look at your power spectral density and you see the slope that it has, and you figure out what alpha matches the slope, and then you can find out what kind of noise you have.
Okay, thank you.
Okay, any other questions? If not, I think we can thank you again
Thank you very much.
and close this session.